information about an event. And if you have orders and orders of magnitude of change in something, like power density versus range, something like that for an antenna, then typically things like power, attenuation, all this are given in dB. So here's the cardinal rule with decibels. When you talk about decibels, the symbol is just D capital B. And what it means is this: if it has to do with power, when we talk about decibels, it'll be dB watts or dB milliwatts. It means 10 times the log. Remember, this is log base 10 of the power. That's just power. Power would be in watts. This would be decibel watts. You follow me? You can do it exactly. You with me on that? Now, if it has to do with voltage or current, then the dB term will be equal to 20 times, and this will be an absolute value, by the way, 20 times the log base 10 of either the voltage or the current. Y'all follow me on that? I'm going to give you some examples. This is really useful too, because you're going to see in a lot of your lab work. If you're seniors, you'll be seeing this more and more. Now, here's what's typically done. For power, we don't do dB watts. What we do is dB milliwatts, and let me show you this. So here's a typical thing. If I have something and I say I have a power of 10, say to the minus 6 watts, I'm just throwing this out there. It's an abstract thing in terms of it's not associated with any real problem. I got 10 to the minus 6 watts. That would be 1 microwatt, right? A typical way to deal with that in dB that's used in your phones, if you look up the information, and an industry standard is, we have something called power in dBm. The sub m is milli for milliwatt. And what that means is, we would take 10 times the log base 10 of the magnitude of power, we divide it by 10 to the minus third. The reason we do that, it normalizes it to 1 milliwatt. 1 milliwatt is sort of an industry standard to measure everything against when you talk about radiated emission power from like a cell phone tower. Now if you look at this, just for a second, for this problem I gave you, right? That would be 10 log base 10 of 10 to the minus 6 over 10 to the minus 3. Agreed? That's equal to 10 times 10 times the log, and it would be base 10 of, log base 10 of 10 to the minus 3, right? Now, if it's a log base 10 of any number, and you have 10 to an exponent, it's the log of 10 is just that any number. You all follow me on that? I'm going to see this right here. With me? Can you see it far back? Okay. So that's just equal to minus 30, and it would be minus 30 dBm. That's typical. Hope I'm answering it the best way. Now this is dB in terms of power. Another thing that's very common is dB microvolts. Do y'all hear me? dB microvolts. There can be dB microamps too, but dB microvolts is used all the time. So if I have a voltage equal to 10, say, to the minus 9th volt, that's a very small voltage, by the way. You're just about unable to measure that. You may not be able to measure it without special equipment. Well, that voltage would correspond to so many dB microvolts. And here's how I think you would get this. So if I want the voltage in dB mu, this is the micro symbol volts, it would be 20. Now it's 20 because it's a voltage or current, not a power, times the log base 10 of that voltage over 10 to the minus 6. Again, when you see anything like dB micro or dBm, whatever that is would be what you divide the original quantity by. I gotta make this clear. This is always a magnitude. Power, you know, when you've had your power course, haven't you, most of you? You know you have? Well, if you have, remember complex power, you would have a real plus J and imaginary power called reactive power. You only care about the magnitude of the quantity. You follow me? So you square the real, square the imaginary, take the square root in order to get the magnitude. This becomes very important. Everybody follow me on this? So what's that going to be? I would have 20. Anybody? What is this going to be? 10 to the minus 9 to 10 to the minus 6 is 10 to the minus 3, correct, class? All right, what's the log base 10 of 10 to the minus 3? Anyone? Minus 3, right? Just minus 3. And if I multiply by 20, it would be minus 60. Agree, class? So this would be 20 times minus 3 or minus 60 dB microvolts. And I hope I answered your question, sir. Did you? Get it? Now, so when you get shielding effectiveness, which really is a ratio of the incident field to the transmitted field, it's just 20 times the log of the incident field's magnitude divided by the transmitted field's magnitude. That's it. Now I want to make a comment about the thing I put. I put an exact solution for a shield for the output of the field value, the electric field value, versus the incoming field value for a shield of a given thickness with given intrinsic properties and a given frequency. Did everybody look at that? That's the exact. 99% of the time, you don't need the exact. The only thing you need is the approximation I'm going to do right now, because this is a natural leading. And I'll do it here. By the way, that was a very good question. So, here's the problem. It's a finite region of a certain thickness, right? B, I'm going to just call it B, right? It has different parameters. Let's assume we can calculate alpha, beta, call it of the shield, and eta of the shield. So we know what those are without, I don't want to go through a calculation, but you know how to get those, correct, class? Right? Sure. And you will keep the propagation constant too if you want. Now, you have an incoming field with a magnitude EI. It's propagating this way. Really, at this point, it doesn't matter about coordinate systems. If you want to, you can put them in. You don't have to. You'll be good at this after a while. All right, now, you know that there's going to be a reflected wave, right? This way. And there's a transmitted wave. Right? Everybody got that? If we wanted to get the transmission coefficient at region 1, call this 1, and call this 2, the only thing we do is take 2, and it would be eta input. Now, I'm going to tell you this. This is eta in, but we can make an assumption. And I'll do it right here. If D is greater than a skin depth, and the skin depth, you know, is equal to 1 over the square root of pi f mu sigma, and that's sigma in the shield. If this is the case, that's a thick shield. The reason I'm saying that is, here's what really happens. You get a wave on the inside here, it's going to attenuate, right? Now think about this. If it's just 1 skin depth, it attenuates down 33% to here, right? In magnitude of the E field. You all agree with that? Now it hits and ricochets back. It attenuates another 33%. You all follow me? By that time, it's less than, I think, 0.1%. You all follow me? The amount of that field that gets out is about 0. You follow me? So if you're at least a skin depth thick, you really don't have to worry. Now, here's what happens. That means this, eta S right here, eta N, simply becomes eta shield. That's what I was getting at last time. You all follow me on that? Now you don't have to worry about that complicated formula that I gave you. You just default to this assumption. And again, I'm saying this, trying to really underscore it. 99% of the time, that's what happens. A shield isn't a shield unless it does that, primarily. Now, if you have this, that means the transmission coefficient is 2 times the impedance you're going into, which is eta shield, right? Divided by eta shield plus eta naught, right? Down here would be eta shield plus eta naught, wouldn't it, class? Now, eta shield, actually, for any decent shield, eta shield is much, much less than eta naught. Eta naught will be 377 ohms for free space, won't it? This will be 1 ohm, maybe. Usually, did anybody calculate this for the shielding problems? Do you remember what it was? Did you? Do you remember what eta S is for the shield itself? Oh, it's very small. Maybe 0.01 ohms, all right? In other words, this parameter is met. So if that's the case, then eta naught down here is, eta naught is dominant. Eta naught plus eta shield is just eta naught. You all follow me? Again, I'm talking about an approximation divided by eta naught. So that's going to be the transmission coefficient from media 1, this is the incident field, to media 2. That means we would take the incident E field magnitude, multiplied by tau 1. Now that would be the electric field strength right here, right? Just on the other side of this boundary. Do you follow me? This is how much is transmitted. Everybody follow me? Can you see it? Okay. Yes. But what's going to happen to it? It's going to attenuate, right? As e to the minus alpha, and right at this point would be the attenuation would be e to the minus alpha d. Do you see that? So now I take this and I multiply by e to the minus alpha d. And what he's going to do is take a magnitude in this, and he'll let that be gamma. But don't worry about that. Just let it be alpha. It's the only thing that has any impact. Now, when I get down to that point, what's next? Now I've got the E field right here. It's reduced greatly from the incident field. It may be 4, 5, 6 orders of magnitude by now reduced. What do I need to do at this point?
Multiply by 2. But
well, multiply by the transmission coefficient, right? So the transmission coefficient right here, what's that going to be? Well, it's twice the impedance you're going into. I'm assuming this is air as well. So it's 2 eta naught over the impedance you came from, eta shield, plus the impedance you're going into, eta naught. Do you all agree with this, class? How many do? This is just a standard equation, right? We've got to know this very well in this class. This is just a standard type thing. That's transmission. It's going to be 2 times the impedance you're going into over the impedance you came from, plus the impedance you're going into. It's just like you did with your transmission line problems. And if you want, just get 1 plus the reflection coefficient here if you don't like this. But either one works. Now, that, you can see that eta naught is much greater than eta shield. So this is basically just 2. And that would be approximately the magnitude of the transmitted field. Are you with me on this, everyone? How many see this? Again, I'm using the approximation, but 99%, yeah. Okay, 99, maybe 0.9% of everything you ever do that has to do with shielding, figuring out shielding, we'll assume this will be a very valid assumption. Now, when I get the shielding effectiveness, I'll put it up here. This is just a measure of how effective or the goodness of a shield, if you will. And it's in dB. This is a voltage, right? It's volts per meter. So shielding effectiveness is 20 times log. And really, it's the magnitude of the incident E field over the transmitted E field. Some of you won't like that. You'll say, why isn't it the transmit over the incident? You can do it that way, but it's negative, won't it be? Right? We tend to talk of shielding effectiveness as a positive number, 20, 30, 40 dB. We always have. It's just an industry type thing. So when you look at this, the shielding effectiveness for the approximation, fixed shield would be 20 times the log. This is again a base 10 log, and I warn you, if you're using MATLAB or Octave, if you type log of a number, it's natural log. You have to type log 10 in MATLAB to get the log base 10, and log 10 and also in Octave. And I don't know if Python requires it. Does anybody know if Python requires that? Anybody here use Python? Wasn't there at least one person that did? Maybe not. Python's going to be very popular. It's free and there's so much out there you can download. And people use it in industry all the time because there's absolutely enormous amounts of toolboxes that are developed for specific problems. If you go to Intel, a place like this, even Dr. New uses Python almost exclusively, or he'll use, I mean, maybe if he has to, he'll use MATLAB, but I don't think he uses. You had Dr. New, haven't you? Didn't you use Python a lot in your class or not?
He used to, but he stopped a few years back from making people use Python in class.
He what?
He stopped from making people like do Python.
Oh, did he? That's unfortunate because that's valuable for you guys when you go out and interview and stuff. If you say you have experience with Python, they'll love you. All right, so what's this one going to be? Well, if I look at this is the transmitted field, right? So I need to take this in the denominator, and the numerator is just EI. So I have EI over 2 tau 1 e to the minus alpha times d. Now you can see, right, oh, there's an E naught here, or EI. The EI's cancel, don't they, class? Right? And you get 1. You just get this being equal to minus 20 times the log, because if you have log of 1 on top, log of 1 is 0, minus 20 log of this, so it's minus 20 times the log of 2 tau 1 e to the minus alpha d, and that's the shielding effectiveness approximately for a thick shield. And this is tau 1. Now, Dr. Wentworth, I think, actually takes this and plugs it into that formula, but that's what it is. Do y'all follow me on this? Remember the reasoning process. Did you have a question on this? Did everybody see this? And that's the way you do shielding effectiveness in a nutshell. Okay? All right. Now, any other questions? This is actually what I'm showing you kind of was what I wanted to do at the beginning of class anyway, so your question was perfect. Any other questions about the homeworks or problems? Anything like that? Okay. You all good? Don't be afraid. Now's the time.
Could you work the example problem you had listed for homework 6? The one that wasn't the book one?
I'll be happy to. Can you just do me one favor and give me the specifics? I don't have to memorize.
Absolutely. So you had eta equals 60 pi, mu r equals 1,
Eta equals 65.
mu r equals 1, h equals negative 0.1 cosine,
H equals, go ahead, say it again.
negative 0.1 cosine, omega t minus z,
Just Z?
yes, in the ax direction, plus 0.5 sine, omega t minus z in the ay direction,
Sine omega t, go ahead.
minus z in the ay direction.
Uh-huh.
And we were to find epsilon r, the angular frequency, and the E field.
What problem is this again?
Hold it,
That's
there's-
homework 6.
Yeah, 6 point.
There has to be something more about, to get the angular frequency, we have, okay, hold on. They don't, did they give you mu relative as
Oh.
1?
Yeah, mu r is 1.
And it's lossless, how can you
It's a
tell?
lossless medium.
How can you tell it's lossless?
There's no.
There's no E to the minus alpha.
Right, there's no e to the minus alpha, and what direction is it propagating, people? Come on.
Z direction.
It's positive z, right? Because if it's minus beta z, right? If it's in a positive z direction, it would be plus beta z if it was in a negative, correct, class? So that means I know what beta is. First, I know the direction of propagation right here is equal to az. I know beta is equal to 1, right? I know it's lossless, correct, class? So if it's lossless, I know that beta is equal to omega times square root of mu naught epsilon naught square root of mu relative epsilon relative. Do you all agree with that? This is for a lossless case, correct? Now if it's lossless, let me just make it life a little easier for myself. Is there an eraser in here, by the way? 1 over, what's square root of mu naught epsilon class? 1 over c, right? C is 1 over the square root of mu naught epsilon, right? So we've got these two quantities out by themselves. We need this. I know mu relative is 1, so I get rid of that. And now I can find epsilon relative from eta, right? Because for a lossless case, eta is square root of mu naught epsilon naught times square root mu relative over epsilon relative, right? You with me on this, everyone? I'm just repeating. I break out, so this is 120 pi. So I have 60 pi, which is given is 120 pi. And this is, since mu relative is 1, it's 1 over epsilon relative here. Now it's simple math. 60 by pi goes away, 60 by 120 is 1/2, is equal to, right, square root of 1 over epsilon relative. Epsilon relative has to be positive. We square both sides. We see epsilon relative is 4, don't we, class? So now we have epsilon relative is 4. Now we know that, I don't want to go through, you all follow? This is straightforward and simple. Now, if we have epsilon relative is 4, I plug it into here, right? I know beta is 1. I know C is 3 times 10 to the 8th, correct? And now I have omega is equal to 3 times 10 to the 8th, right? It would be C divided by square root of 4 or 4. Or omega is equal to 0.75 times 10 to the 8th meters per second, or 7.5 times 10 to the 7th meters per second. And what else do they want?
The E field.
All right, I'm just going to ask you this now. If I wanted the E field looking at this, and I have eta, what do I do in general? What's the relationship?
You divide.
I know that E over H is eta, right? That's the general, most general way to express it. Well, I've got eta is 60 pi, don't I? So when I come here, I'm just going to do this. I know H will be orthogonal to both the direction of propagation, right, and the E field. You all agree with me there? It means E, use your right hand, E in the direction of my index finger, cross H, direction of propagation. I know it's going in Z, right? I don't know the direction of the E field, but I know the direction of the H field here, right? The H field's in the minus X direction, isn't it? Think about that. So what I need is something crossed into minus X that'll give me plus Z, right? So it'd be minus AX minus AY equals plus AZ. Do you agree with that? I'm going to see this right here. Just do it in your mind. So this would have retain the minus sign, but it would be 0.1 what? Times eta, correct? If I wanted to get the E field, it would be minus that eta in right here. And then this, I'm going to switch it to E. I'm trying, I guess, save things. Instead of AX, it would be AY. I hope you appreciate, I'm not trying to confuse you, I'm trying to save time. In other words, what I've done is, I've taken this quantity, multiplied by 80 to get the magnitude of the E field. To get the sign, I use the right-hand rule. I know it's propagating in the Z direction, and the orientation of H was minus Y, right? So X would have to be minus AX, so there's a minus sign. Wait, that was AX, right? Right. All right, so, yeah, wait. Hold on. Now I'm thinking about this. This is the direction of propagation. That would be x, that would be y. We had originally that is minus ax as the h. That means, yeah, it would be, the E field would be minus ay. That's correct. So that's right. Now for this one, to get the magnitude, I have to take 0.5 by eta. Do you all agree with that? Just to get the magnitude. So I come here and I'm going to put the eta in. All right, now about the sign. That's positive ay, right? That's the H field. Think about it. H field positive ay means E field, in order to go ax, E field would have to be minus ay, right? Or minus ax crossed into ay, right? Wait a second. Oh, I'm sorry. The E field, the H field was that minus or plus? It's plus, I'm sorry. H field's plus. So if the H field's plus, if we have you know what? I drew this wrong. This has got to be a right-hand coordinate system. So if this is x, and this is y, x crossed y is the direction of propagation, this would be z. So for that one, we had positive ay, so that means positive ax crossed and a positive ay would be positive z. That is positive there. And we originally had a minus x, so for H field. Yeah. So the H field itself was minus ax, and it would be minus ay. Yeah, that's right. Okay, so it's minus here, plus there, and these would be the values, and this would turn into an ax here. Y'all with me on this, class? That's the rationale for doing this. I could do what? Turn these into phasor quantities. And if I had the H field to get the E field, I would have minus eta, AP direction of propagation crossed into the H field. Remember those two equations? That's how I get it. How many understand that? All right, you good with this one? Thank you very much. Any other questions? All right, what I'd like to do is start perpendicular polarization today. And what I'm going to tell you, because do you have your books here? Yeah.
I have a quick question, just on, what problem was that?
It was the one in the OneNote.
One note
Oh,
problem.
it's the
It was-
OneNote problem? Okay.
It's a good problem though. I want to tell you one thing. On page 359 in the book, it starts with oblique incidence. It starts with the T polarization. I'm going to do a little of this, and I'll give you a quiz. I know you're anxious. My heart. It's closed book, closed notes. You get your calculator, and that's it. No wearable electronics. No phone a friend. And I'll spread people out a bit more. Unfortunately, you're supposed to keep that 6-foot perimeter, but it's hard. You're pretty spread out. I'll probably spread some of you on the other row there. And not right now, but in a second. So this is going to be oblique. And in the book, the drawings I'm going to be looking at are on page 360. And so when we talk about oblique incidence, I want to use Dr. Wentworth's representation, what he does. He says we're going to have two media. This is media 1, media 2. They have the usual intrinsic parameters that you don't need to worry about that much, but they'll have some beta 1, some beta 2, eta 2. All right. We'll do this with lossless at first. And the reason is because it gets a little complicated. We're going to assume the wave's this is the positive z-axis. Assume this is the x-axis. And this is the center of the coordinate system. Now, if you look in his book, what he does is have a picture in figure 620. And we're going to talk about what's called the transverse electric polarization. It's symbol TE polarization. So when you do that, now the wave is not, this is region 2, that's region 1. The wave is not coming in normally incident, it's coming in at an angle. So this is the angle of the wave, you have the transmitted field. And they're going to assume the E field is actually pointing out of the board. So this is the incident E field, it's out of the board. Can you all appreciate that, like the marker? Follow me? That means if E cross H is the direction of propagation, the H field would be in this direction. Right? Can you all appreciate that? Now, it's propagating in that direction. So what would an equation be for E? Here's where it gets a little hairy. Well, the E field itself would be equal to some E naught. Remember, it's perpendicular coming out of the board. The E field would be oriented in the AY, let's see, yeah, in the AY direction. I'll put that out here. Then it's going to have the E to the minus J beta 1, and here's where it's different. Now we put a term Z prime here. And here's why. Well, that's the Z-axis and that's the X-axis. But we're saying this is the Z prime direction. Do y'all follow me on that? Z prime is going in this vector direction. Then we take a look at some information that helps us. Dr. Wentworth uses this as the angle. He says this is the angle of incidence. I want to tell you this. What he's really saying is that angle right there is measured from the perpendicular of the perpendicular to the two boundaries. This is region 1 and 2, two different materials. Some other books will use this angle. I just want to warn you, if you're looking at Chegg or any stuff like this, I'm going to warn you, you'll go nuts because they'll have all sorts of proofs and stuff like this in solutions, and they'll have completely wrong angles. Just remember that, okay? I would encourage you to be very careful of external sources right here. You get terribly confused. Even when they use Wentworth's book, they probably have the wrong solutions because of that. So when they do that, what it means is Z prime itself is actually given as X times the sine of the angle, beta incidence, plus Y times the cosine of the angle, beta incidence. Some of you are going to say, how did you know that? And that's a very good question. Remember that this would be the angle theta incident if we're talking about a wave propagating this way, right? I'm trying to just show you this. This would be the Z component. I'm sorry, I put Y there. This should be Z, my bad. That's a mistake on my part. This is Z, and this would be the X. Now just think about this. This would be like Z prime here. Try to appreciate, I'm doing my best here to show you this, but it will get a little confusing. If I go any distance in this way, that would be Z prime, right? How does that translate to a distance X and Y? Well, if you think about this, draw perpendicular. Right? Here I have Z over this distance would be, if you think about this, that angle right there, these are opposite interior angles as this angle, isn't that right? Think about when you had correct class? Well, what Z would be, if I take a look at this as hypotenuse, Z, right, times the cosine of theta incident would be equal to this position right here. Do y'all follow me? If I take this times the cosine of this angle, I get this distance, correct? Can you see it? Play around with this triangle if you can. Then, this is the hypotenuse, and this is the distance I want. Well, X divided by the opposite side, right there, would be, just look at it this way. This is the angle, right? If I have opposite, right? This angle would be this angle too. And this opposite over this, this is hypotenuse. Hypotenuse over this side would be the sine of that angle. So this distance would be simply z times the sine of theta. And when you add them together, you get this. You can play with this at home. Usually it takes a little time to struggle, and I'll put this up on OneNote so you can see it, all right? But this is the truth. So this is equal to z prime, and I'm about out of time. What time do you have, guys?
12:34.
All right, the class is over at 12:50. All right. Let me just say one thing. This is something, you're gonna have to look at this and prove it yourself. The easy way to do it is make z prime 1, and just see what this side is and this side is. Square both this side and this side, take the square root, you'll prove in fact it is that, okay? And you can prove it to yourself. But now when we talk about a unit vector in the direction of propagation, this is important. Here, normally when you get unit vector, you take vector z prime, right, over magnitude of vector z prime. When you do that, to save time, this is what you're going to get. You're going to get sine of theta incident AX plus cosine of theta incident AY. AZ. Pardon me. All right. And let me just say one thing about this, so we can go to the extremes. This is the way I do problems when I'm in your position. I always look at what it should default to if I go to the extreme. The extreme would be when that incident angle is 0, then it's normally incident, isn't it? You all see that? When the angle is 0, that wave's normally incident, and the direction of propagation should just be AZ. Do you agree with that? Well, if we come here, if we make the angle 0, sine of 0 is 0. Cosine of 0 is 1, it is AZ. Do you follow me? Do the other extreme. When the angle is 90 degrees, now it's going up this x-axis, correct? All right? Sine of 90 is 1, AX, plus cosine of 90 is 0, it's straight up. And in fact, it does work for all cases. So I want to tell you it's proven. And that's the unit vector. Now, I'll just tell you this. That isn't, this is still going to be AY, but here's the catcher. When we get H, and I'll do this next time, H incident, I take it equal to 1 over 8 in region 1, then I take that unit vector I just solved for, and I have to cross it with the incident E field right here to get the H. And here's what I'm up to. I'm going to get the E field components on this side of the region and that side of the region, and equate the tangent field values, make them the same, and then solve for reflection and transmission coefficient. Okay, now I'll give you a quiz. Okay, class, could you take you and Miss, could you just move over to those seats, please? You can stay there. Ashley, you can stay there. And would you take everything off your desk, except your calculator, and if you have any wearable electronic